So if you guys remember, we start from like brief introduction of machine learnings and ANNs. We move from machine learning to multi-layer perceptron, ANN and CNN and RNNs. So I guess we kind of covered the basic stuff in under the topic of deep learnings. So from now on, I'm gonna show you some like the application perspective. So the first topic is anomaly detections. So I'm gonna like show you what is anomaly and what is anomaly detections and how can you utilize the things that we learned in machine learning or deep learnings with respect to anomaly detections. So it's gonna be like focusing on like how to utilize an applications perspective. So first of all, let me talk about definition of anomalies. I mean, anomalies is all same as the outliers. Probably outliers must be familiar with you guys. And so essentially those are the same thing. I mean, I don't think I need to give a like strict definition of outliers or anomalies and some kind of object that are different from the most other things or other object. Those are the outliers. Or something that deviates from what it is or what is standard or from what we expected. I mean, this is kind of the figure that we can easily see. Maybe, I guess that fish is kind of, we can consider or treat it as outliers or anomaly because of, I would say, because of color or because of the direction that the fish heading to, right? We don't need to give a specific reasons why, but we can tell for which one is outlier. And let's talk about some kind of causes of outliers. And the data from different class of object or different underlying mechanism, like disease versus non-disease, it could be outliers, or fraud or non-fraud. Okay. A lot of, like in internet or social networks, we need to detect like anomalies or fraud detections, things like that. I mean, I guess it's not that difficult to understand. Or data measurement or collection errors. If you have some mistakes, if you made some kind of mistakes when you collect the data, we can treat it as outlier. Or another thing is sometimes the outlier is natural variations. You know why? Because if we assume that the kind of data supposedly follows the Gaussian distributions, and most of it's gonna be like fall into these around the center. But we do have some chance to get outliers, but in this case with a small probability. But still we have. So it takes on the Gaussian distributions. So sometimes outliers is kind of natural way. And this is the probability density functions for standard Gaussian distributions. And assume that you all know already. And we talked about the definition of our anomalies. Now we want to detect. We want to know, hey, this one is normal and this one is outlier. So we call it anomaly detection. And basically, we want to find out the outliers. All right. And here we do have two figures. The first one is like, say like x of 1 and x of 2. And it doesn't have to be two dimensions. And say we plot in the data in high dimensions, whatever. And I don't know what the physical meaning of x of 1, x of 2, it doesn't matter. But if you plot them, the green dots, I mean, most of the data points are located around, and you can treat it as a normal data set. And somehow, we don't know why, but somehow, like here in red dots and data points, kind of far away from these green groups. We can treat it as outliers. Don't worry about how to detect or find out. Don't worry about it. We're gonna cover it soon. All right. In this figure, is kind of the thing is that we have the data set. We have to extract the features first. We have to extract the features, and if for example, if two features, that means we can plot it in two-dimensional space like this, right? But it doesn't have to be two. It could be the data points distributed in higher dimensions. In that case, probably we are not able to plot. So in that case, since we are not able to plot it, it's not intuitive to find out which data points is outliers, which data points are normal, belongs to normal groups. Okay, that's the first case. And the second case that second example that I can give you is, think about the time series data set. I think we discussed a lot, starting from time series data set and how to analyze the time series data using the recurrent neural net or RST and things like that. And single data points or some few data points, probably we can, hey, that's some outlier data points among the sequential data set. And we don't know what it is, but it's kind of suspicious that something happened around that time index. Okay. If we have this kind of definitions of anomalies, it's really with respect to points. Or another, the concept of outliers. Say we do have some kind of data, sequence of data set, most of them. And somehow, like this one is, we can treat it as our outlier sequence. Right? Doesn't have to be single data points. So those are some kind of the examples that we can think of when it comes to anomaly and anomaly detection. Yeah. Before that, let's think about what kind of application that we can have related to anomaly detections. I mean, here, like, let's see this one. This one is outlier, right? And let me see. Probably like you can treat it as outliers. I think the people are fighting. So in security or surveillance, probably sometimes we need to, is required to be able to detect some kind of outliers or anomalies for the purpose of security or surveillance, like autonomous things. And another applications that we can think is related to biomedical applications. We can have tons of anomaly detections. I don't know, I'm not expert, but say this one is kind of normal, like, and this one is some kind of disease. When you diagnose something in a hospital, it's anomaly detections. Most of the anomaly detection work is going to be done by medical doctors, right? But nowadays, a lot of AI tools can apply to help the medical doctors to support them to make better the decisions or accurate decisions. Another application is like a lot of industrial examples you guys can think of. Like for example here, damage detections and a lot of mechanical components here, like gears, and as you can see there is some kind of defect on the surface or crack. Of course you can see like through the naked eyes, but we want to do anomaly detections based on the collect or gathered data set. It could be like vibration signals, like that. And similar, and another one is machinery defect diagnostics. And suppose we have this kind of like rotary machineries, or I'm not sure what's compressor, pump, whatever. And suppose we have like 100 pump or 100 compressors in my plant. It's almost impossible, or it's extremely cost to do machinery diagnostics by the expert, by humans. So it's a lot of needs from the industry. Anomaly detections. We want to detect if the machine is not operating in a good conditions. That means it's outliers, right? So we want to detect as early as possible. So we call it early alarm systems of malfunctions of whichever mechanical system. Those could be the good examples or applications of anomaly detection. Now let's talk about some of the difficulties related to anomaly detections. Okay, what kind of difficulties that you guys can think of? We learned supervised learnings and unsupervised learnings. And for outlier detections or anomaly detections, if you want to do anomaly detections based on the data and apply either machine learnings or deep learning method, what kind of difficulties that you guys can expect? Suppose we have some kind of machinery or mechanical systems. You put some sensors on it, you measure it. Most of the time, the data set, most of the time, collecting the data while the machine is in good condition or good operating conditions, right? So that's one class, like say normal operating conditions. And suppose you want to apply supervised learnings. That means we need data, labeled data in another class. But if that's like faulty or malfunction systems or anomalies or outliers, in most of the case, that's not going to happen, right? So that's we call it scarcity of anomalies. It's not easy to get labeled anomaly data set because anomaly rarely happens, right? So I don't think it's supervised learnings in anomaly detection is not a I don't think it's a good option. Another issue, I mean, pretty much the same issue is the overfitting issues. Remember, if you have a small data set, always you have to watch whether your AI model is kind of suffering from overfitting or not. Because in many cases, anomalies has only small number of data sets. You can, I mean, for sure that you guys can assume that anomalies related data set you don't have, or extremely small number of data. So supervised learning is probably not a good choice. You can have, right? You might have some like your machinery failures. You can have that, but the related data set is extremely small. So if you decide to apply the supervised learnings, you're gonna have huge imbalanced data set. That's kind of the most significant severe problems or difficulties that we have related to anomaly detections. That's the first one. And the second thing you can think of is diverse types of anomalies. What do you mean by that? Say that there are so many causes of anomalies. Say, hey, let's think about this computer. This is normal conditions, right? Now it's operating. But you can have many different faulty types. There are so many. There are so many reasons that for the malfunctions. And I guess the figure represents that kind of. There are so many components on it. Even I mean in car manufacturing or assembly process. All the mechanical component, all the components can fail. Right, there are so many. And another, like here, say we have, I guess we have dogs and chickens, and we don't know which one is anomalies, like this one and this guy. And it's kind of difficult to tell. And if we decide to, again, it's supervised learning, at the training stage of a neural net, we are not able to have all possible anomalies as the input, or input and the associate labels. Why? Because it's scarce and we have many different types. That's why that's not easy. Okay, so far I defined what kind of anomalies and definition of anomalies, outliers and outlier detections, and the applications and examples, and why it's difficult and challenging issues. And now let's attack how do you solve the problems. So there are the first one, or probably these are the second or third. I'm not sure. So the first one is supervised anomaly detections. Of course, we can use that. Say, if you're lucky enough to have all the labels available for both normal data and anomalies. In that case, it's pretty much same as classification problems. But it's most likely within high class imbalance issues. Right? Most of the case, it's going to be the data that we have is normal data set. So again, like I said, supervising is not a good choice. And let's see the second case. Or let's see the third case first. So it's unsupervised. That means no labels at all. So only thing that we have. Let me see. Let's see the second case first. Semi-supervised. That means we do have labels available only for the normal data set. Okay. I mean, normal data set is not difficult to collect and label it because we know that the system is operating right now without any problems. So it's a semi-supervised. Unsupervised, on the other hand, is we don't have any labels at all. Okay. And those are the data labels that we have, and we're gonna do something with these data set to conduct anomaly detections. Suppose we did that, and then what's the expectations or output of anomaly detections? Let's see. I mean, we can have labels. What does that mean? That each test instant in the data set is given. The output is gonna be whether this data belongs to normal or anomalies. It's like a supervised learning, like classification problems. So again, here same as the typical output of classification-based problems. So the anomaly detections output is gonna be, hey, this. I mean, in real time, it's in normal conditions, and suddenly it's gonna say, hey, something's wrong. You have to watch. You have to do something. That's the first one, and like I said, same as classification problem. Another perspective or approach that we can think of is score. What do you mean by score is that for each test instance is assigned anomaly score. So it allows the model, if we do have a model, then model allows the output to be ranked in order of anomaly scores. I mean, let's say this is like normal, and 0 is like abnormal, and the output of anomaly might have some kind of scores. If it's close to 1, that means it's normals, and if the other ways, then that means that it's relatively like it's not normal. So instead of like doing binary classifications, the model can give the scores at the end as a final output. If you do have scores, then we can have additional threshold parameters. I'm not sure. Just for example, like say, if that's the score is smaller than 0.4, we have to do something. We have to watch. We can consider it or treat it as outliers. I mean, something like that. Another issue is how do you set up the threshold? That's another issue in the problems for scores. Okay. And a lot of different variants of anomaly detection problems. And the most common thing is, as you can see, there are probably like 3 different. So suppose with the given data set D, all of them these are the common. And you want to find all the data points with the anomaly scores greater than some threshold. That means we want to find all the data points which we believe that's anomalies or outliers. How? Because if you have predefined threshold, if that's greater than or I don't know, it's greater than or smaller than whatever, then you can consider that data points are outliers. Or find all the data points having top n largest anomaly score. Based on the scores, we can order them. Right. The last one is testing data points. We can compute anomaly scores with respect to D. We can compute like anomaly scores. Not that difficult to understand, I guess. So let's move on to actually how you do anomaly detections. And I'm going to introduce, actually there are typically in anomaly detection 3 different ways. First one is using the statistical approach and machine learning approaches and deep learning approaches. Right? But I'm going to cover statistics and deep learning models. And machine learning, I decided not to include here. So let's see the statistical approach on the anomaly detection first. I mean, the statistical approach is not the scope of this course. So just, here, let me move on to basically this one is that I want to introduce. Right? Before that, there are some traditional way or statistical way that I want to share with you. So anomalies or outliers that are fit poorly by the statistic models. So we assume that it says in data points like this. In statistical perspective, we believe that we can fit the data distributions, and we do have probability density functions to represent the given data points. Okay, and so we believe we are able to estimate parametric models describing the distribution of the data set. Okay. Now we do have we do have probability models, and if this is data points, then we can compute that data points. We can compute the probability that data point is coming after that. These the probability density functions, and I guess that probability is going to be extremely small probability of that. Then we can treat it as anomalies. You guys know what I'm talking? Okay. It's like apply the statistical test depends on properties of test instance, parameters of models, and mean and variance, or I guess the typical approach is we can assume that it's Gaussian distributions. And we can compute the confidence limits. I'm going to show you in the following slide. So the easiest one or the simplest one is if I have one-dimensional data points, data points in one-dimensional space. And again, it's assumed that data points, we can model it or we can estimate it. Univariate Gaussian distributions like this. And this is the standard Gaussian distribution, Gaussian probability distributions, like that. And the data set that you have, assume that the current data set is from the normal conditions. And if you make assumptions, which is that the data points follow the Gaussian distribution, then you can do this you can compute the z-score. And this is in data is in x. You can subtract the sample mean and divide by the sample variance to normalize it. So we call it z, and assume that z follows standard Gaussian distributions, and you can plug into this equation. Or there are some lookup tables that you can look for. And if that probability is like around here, that means the current data points or testing instance are like kind of within the confidence of the Gaussian distributions. Or if that's extremely like in outside of or tail, that means that probability is gonna be small, and it depends on how you set the threshold, but in this case, you can treat it as outliers. That's kind of the basic concept or approach or method. This is what I'm trying to do. Again, we have a bunch of normal data set and trying to fit the Gaussian distributions. It doesn't have to be standard. And we do have testing instance. I want to know this data points is outliers or not. And we have to compute z-score, or we have to compute the probabilities, basically. If that probability is around here, it's a reasonable to say this is kind of the same as the data set that you have, which is normal. And if it's extremely outside or small, that means something different from the normal data set that we have. Then we can make some kind of conclusion that is kind of outliers or different from what we have. That's univariate. It's one-dimensional space. And of course, we can expand it, the same conceptual things to the multivariate. What if we have multidimensional space? Basically, it's the same. In that case, just to visualize, say now we have the data points in two-dimensional space. We have a bunch of data points, normal, like that. Here, in this slide, basically what I want to do is that I want to introduce the concept of Mohala-Nobis distance, right? So some of you already know, but most of them it's new or first time. So let's see what it is. And in terms of distance, we have Euclidean distance. In the Euclidean distance, say this one is kind of the blue data points is a normal data set, suppose, and we plot them, and we kind of know that distributed in that way, kind of ellipse, and we collect some other data points, say it's red, and another one is green. We can group it as A and group as a B. In terms of, suppose this is kind of the center points in blue data points. In A, data points in A, data points in B, and if you compute the Euclidean distance in two-dimensional space, it's like 5.7 and 7 is pretty much the same. Okay. So in the Euclidean distance, A and B kind of from the center from this data point, in this point, I mean, the distance are pretty much the same. Right? But actually, that's not the correct way of thinking, because the blue data points we got this way. That means in these directions, right? It's kind of condensed, and the other ways we have large variance. So in the statistical sense, A is kind of way far away from the center compared to B. You kind of see what I'm trying to. If the data is kind of the if you suppose we have blue dots, like kind of the circle shape, that means we don't have any preference on the directions, right? The data set that we have. In that case, probably Euclidean distance is same as statistical distance. But the data that we have right now is kind of located that way. That means the distance in these directions and distance in that direction has different weights or different significance. Right? So in this case, it's not correct to use a Euclidean distance. We have to use another distance, which is Mahalanobis distance. How do you compute that? The information that we have to know. In this way is condensed, and the other way is kind of spread out. How can you know? If you know the covariance matrix. So we have to compute it. Okay. And we have to do some inverse of covariance matrix here. I'm not going to explain in details. And if you don't have inverse of a covariance matrix in the middle, is same as Euclidean distance. But if you do have this one, this is Mahalanobis distance. It's kind of normalized it, so make it in kind of it's ellipse. But if you do inverse of covariance matrix, you can kind of make transformations, like kind of we have invariant of directions, right? So that's the statistical anomaly detections. And pro and cons. The statistical testings are well understood and well validated. So it's kind of traditional approach. A lot of research has been established and done. And quantitative measure of degree to which objects is outliers. That's kind of the good things. Bad thing is that data may be hard to model parametrically. So we have the example that we have is that here we kind of assume that we can fit the data points with the single Gaussian models, but that's not always true. So and another thing is that we assume the kind of density probably is kind of constant or fixed, but sometimes the density is going to be changed over time. That's another issue. In high dimensions, it's not easy to estimate the true distributions. It's not insufficient. So there are a lot of some kind of issues as well. Okay? That's why I want to introduce deep learning based anomaly detections. So again, the statistical is not going to be the homework assignment. It's not going to be in the final exam. So the only reason is that I want to just go through all the traditional method related to anomaly detections. But this one is the thing that I want to discuss with you. So I want to do anomaly detection since now, because we learned something on the deep learning models. So I want to use deep learning models anomaly detection as one of the examples of that. So let's see how the deep learning researchers kind of think to do the anomaly detections. Any ideas? So since basically you learn all the necessary materials related to deep learning topics. Now, if I ask you to come up with some nice models can perform or conduct anomaly detections. Okay? So let's see how the brilliant people are doing it. And suppose we have only normal data. Okay? And we trained autoencoder. You guys remember autoencoders? We use autoencoder for dimension reductions. In machine learning, we have principal component analysis for dimension reductions. But in deep learning version of PCA is autoencoder, because we can do dimension reductions in nonlinear fashion. And also good thing is that normal data we can assume that it's always available. We're going to use that normal data set to train the autoencoder. So the trained autoencoder will only capture the features of normal data set, because that's the only data set that we feed that to autoencoder network. Okay, so we're going to have some kind of autoencoders. So we're done with the training, all the weights and bias, we compute, and we fixed it. Now, we're going to test it with normal data set. And in this case, in testing, we might have some anomaly data set as well. And I'm going to show you here I thought what kind of normal data set, and I thought we can have time series data set, but in order to visualize, I got the data from the MNIST data set. So assume that 7 is normal, okay? So we do have a bunch of 7 digits, bunch of them. And this is normal. We can construct the autoencoder and feed that all the different 7 digits, and we can get autoencoder. Now, when you do testing, we assume that anomaly is 5, right? So we feed this. We take this 7 as an input, and we can feed that the 5 into this autoencoder. Any ideas how we can use the anomaly detections? How we can detect whether we got 7 or whether we have 5 into our input? You see what I'm trying to do? Since we're gonna decide to take MNIST data set, I'm going to use convolutional autoencoder, same as the autoencoder. The only difference is we're going to take the image as an input and we're going to reconstruct the images. So you can think as autoencoder with a bunch of 7s. We're going to train. Now we're done with the training. While we are testing, we put 7 on it. Then we will get the autoencoder is going to produce or generate something which is reconstructions, right? And since this autoencoder see many 7s, so I guess the reconstruction performance. What do you think? Reconstruction performance of 7. And what if I give 5 as an input to the autoencoder? Then the reconstruction performance is not that good because the autoencoder never have been seen the 5 before. We can treat it as an outlier, right? So although we have 5, this is the reconstructed data set. Okay. So this is the idea of, hey, now I can compute reconstruction errors. Right? We can relate it to the reconstruction errors to score of anomaly detections. Okay? Because since we trained the autoencoder only with using the normal data set, so it's reasonable to say that it's a normal data set is going to make good reconstruction outputs. But for anomaly data, the autoencoder perspective never seen it before. So as you can see, still they're trying to reconstruct 7 niche like images or data. So this one is totally different. So this is for training normal data set and reconstruction loss, and we trained convolutional autoencoder, what we call autoencoders. And for testing, we can give normal or anomalies, and going through the convolutional autoencoders, we can compute the anomaly score. I'm gonna define how we defined the score in the following slide, and based on this score, we can make decisions whether the current input is normal or the current input is anomaly. So the last one is how we define the anomaly score, like that. So let's see. I mean, of course, we have to relate the anomaly score to reconstruction errors. So if you have that testing data set, and suppose this is reconstructed one, and if you subtracted it from the input and output, right, and this is the difference is going to be the reconstruction errors. Out of this, we have to come up with one values, scalar values. One way that we can do is this, since this is the image, like say, this data is 28 by 28, we can flatten. And this is flattened column vector. And I want to know the strength of this vector, which we can use 2 norms. In all the elements in this column, all the elements in this column, we can square and do summations and divide by and take a mean. what if the data and reconstructions are exactly the same? Then we don't have any reconstructed errors, right? All of them are zeros, right? In that case, this one is gonna be 0. If the test and reconstructions are different, then we might have some non-zero values here. Then we're gonna have large values. So for that, based on the single values, we can make histogram. And if that's the zeros, then like since all of them are positive, I guess like these are the normal data distributions, and like the anomalies have large value in terms of anomaly score or in terms of reconstruction errors. So that's the idea of, so we use the concept of autoencoder. Since we have only normal data set, we're gonna use that normal data set to train the autoencoders, right? And like I said, if you have normal data set in the autoencoder, pretty much it's gonna have good reconstruction. It's gonna demonstrate the good reconstruction performance. But for anomaly data set or outliers, it's gonna make big difference. You see the ideas? So I guess nowadays for anomaly detections, using this kind of concept is kind of the common things. So a lot of researchers and trying to do this. So let's do the anomaly detections. Let's implement it. So basically, I'm going to show you the same example here. So use convolutional autoencoders, and in this case, we're going to assume that handwritten digit 7 are normal, and we have anomalies 5, and these networks are exactly the same that we learn in convolutional autoencoder. So we have combo 2Ds and combo 2Ds and combo 2Ds, and in encoder part, and followed by decoders, we have combo 2D transpose and transpose and transpose. Okay. And these are the latent space. Latent space, actually, you don't have to see. These are the blue is normal data points. Abnormal data points is like recolored in our orange. And the thing is, we have to see the reconstructions. We have to see the output of autoencoder. And here and these are different. I mean, although we feed the 5 into the autoencoder, trying to reconstruct like 7, because that's the only thing that the autoencoder knows. Right? This one is kind of never seen it before, never seen. So it's a huge difference. And we have to set the threshold. It's kind of the user have to define it. And if you got bunch of data points, we tried it, and these are the reconstruction errors. And most of the blue one is like below 0.05, and most of the outliers kind of above that. Of course, we have some kind of Of course, it's not like 100%, but that's fine. Okay. So we have to define the threshold, whether it's reconstruction errors is greater than or smaller than, based on those the comparison, we can tell this data points is outliers or anomalies or it's normal. So that's the concept of outlier detections. Utilize the concept of deep learnings or autoencoders. Okay? So I'm going to show you, let me see. Oops. So, let's see. So we got the MNIST data set from the, and here is available. And these are all the data points that we have. Now, only the digit that we need is 7 and 5. So I'm gonna get the 7 as a training data set and testing data set because we have to train the convolutional autoencoders. And in order to test it, we need 5 as well. So these are normal train X and the normal train Y, and testing X and Y and testing Y. And these are the shape we have. These are the number of data points that we have. And let's pick randomly. And these are the handwritten 7 we treat it as a normal. And 4 examples that here. And these are totaling 5 as you can see. And let's build up the models and the autoencoders, right? Convolutional autoencoders, like this. And for decoder part, we do have. Now we have to put the output of encoders we feed to the decoders to make it. So now this is the model that we have. And since it's, this is not difficult to train, so just use the atom optimizers. And we want to compute the reconstruction errors, so it's a mean squared errors. We define it as a loss. And we can do model fit. Now we trying to update all the bias and weights to reconstruct the convolutional autoencoders. But remember, at this moment, only thing is that it's 7. So it's not, in this approach, since we don't need to show any like outlier points. So it's I can say this is unsupervised learning, right? Or semi-supervised. So we want to see latent space. Actually, we don't have to see it, but so these are the latent space, and all the 7 normal data, and these are, but here actually we don't have to see the latent space. Only thing is that we have to see reconstruction, and we have to calculate reconstruction errors to compute the anomaly score. And we tested it and plotted. So this is the input data set. We feed in the normal, and this is reconstructed images, and we compute. This is the reconstruction errors. Okay, remember, like this is 0.017, things like that. Now let's feed abnormal data points, which is 5, and of course, see that this is the anomaly score, like 0.1, and here 0.017, things like that. So we have to kind of set the threshold between. Okay. Now I did a bunch of them. How many? Like I tested with 200 data points, and I set the threshold. I mean, always we can look for the better the values, but here based on these two, like 1.1 and is like 0.01, so I just set it as 0.05 as a threshold. Why it's gonna take, yeah. So as you can see, like most of 200 data points located, and most of the outliers, right? You can set the threshold to get, like, to see your performance. Good. So, okay, so that's all I have. I mean, I guess this one is the kind of, say, we start like looking at kind of the applications, right? So that's kind of the first applications I decided to show you, the anomaly detections using the concept of deep learning. Especially I use the concept of autoencoder. Right? Any questions? If you don't, I'm gonna stop here. Okay?